Hello everybody, welcome for our second tutorial on extreme variability. Right now we'll talk about what extreme events are. The objective of this tutorial is to discuss how to make empirical return periods, how to compute them, and then how to plot those with return values to make very nice plots of extreme events. But before we do that, we need to just look back quickly at the previous tutorial and see how we did exactly again. I introduced you to this data set of average daily temperatures in the build in the Netherlands, which gave us this really nice distribution plot where we could see the probability of finding a certain temperature on any random day. As you can see, it's very likely that it will be around 10 degrees Celsius. That's where the highest, where the graph peaks. However, it's very unlikely that we will find 30 or minus 50, which is where we find the tails of the distribution, where our extremes are at. However, tails are not very specific, right? So we want to maybe make or find a way to judge extreme values based on a quantitative way instead of qualitative way of where the tails are. So let's say that we have this data. One of the first things that we can do is, instead of looking at the distribution, make what we call a block maxima record. That's something that looks like this. Every year, every block of time, we pick the most extreme temperature that we find. A block can be anything. It could be a day, so you could take the most extreme day, or in a season, or in a decade, whatever systematic set of time you use. In this case, again, we took the most extreme temperature that we found on that day. And then if you look at that, you see already some interesting patterns. For example, there are quite a bit of 28s and 29s in there. Any value between 28 and 30 is pretty likely to come. However, there's one that gets close to 34 degrees. Well, so not all extremes are the same. There seems to be some degradation there. And that's important to remember, because what we're going to do is we're going to find what we call the X-year event. The X-year event is an event, could be a temperature value or a storm, flood, or a drought that we expect to see at least once every X many years. And this is a value that's often used in policy making, infrastructure development, any sort of those processes. Very important climate change. For example, if we build a culvert, we'll sustain a 500-year storm, a storm that we only expect to see every 500 years. Pretty rare, pretty extreme storm event. Or if you go to the whole end of the spectrum, when we talk about nuclear power plants, you of course don't want those to shut down or break, or what happens to those. So they should be able to sustain at least a 10,000-year coastal storm. This is how these principles are used. Now, this is something statistical. It's a statistical concept. So when I say we expect to see every 100 years, I don't mean to say we will only see one. It's a probability. There's a chance that you only see one, but of course, a 100-year storm has a 1% chance, whereas a 2-year storm has a 50% chance of happening. We at least expected to see every year chance. Now, how can you compute these return periods? There are two main ways. You could either use do an empirical computation from block maximum record that we had, or we could use our distributions that we already designed in our previous tutorial. Here, for this first one, I'm going to introduce you to the empirical method. In a later tutorial, we'll talk about the distribution. So how to do this? First, you get your record, like you see here on the left. This is the same temperature record, and you start ranking all the values, where the value that's the largest, highest annual maximum temperature gets a rank of 1, and the value that's lowest gets a rank of n, how many years you have here. I think here we have 122 years of data, so that will be number 122. You can, for example, already see that 28.2 in 1913 has a very low rank, or it's 109, whereas a higher rank is, for example, 1911, almost 34 degrees value, which is a rank of 14. It means also that there are 14 more ranks. That gets us to our next step, computing the exceedance probability. The exceedance probability is a probability that our value will be exceeded in any given random year. For example, 35, which is a pretty high temperature in the Netherlands, is a low exceedance probability. Any random year, we don't really expect it to be larger than 35 degrees. 28 degrees, however, has a low exceedance probability. There's a pretty high chance that that temperature will be exceeded in any random. We can compute this by dividing the rank by the total amount of years plus 1, meaning that if our rank is really high, the exceedance probability will be pretty high as well. Whereas if our rank is pretty low, then the probability will also be quite a bit lower. We can see that, for example, when we look at 1911, which is rank 14, which then also has a lower probability. And when I say high and low rank in this case, I of course mean the actual number being high, not one being a higher rank number and low. Then finally, we need to compute our return period. To do this by dividing the exceedance probability by 1, or 1 divided by the probability exceedance probability. If you had a high exceedance probability, it was very likely that our value was exceeded in any year, then the return period will of course be low, because 1 divided by a higher number is lower than 1 divided by a low number. If it's a low number indeed, we have a high return period. For example, again, if you look at 1911, we see that the return period is 8.7, compared to 1908, which is a rank 103, that return period is 1.2. So this is how you then have your return periods. Now we know what the return values are, the value associated with one of those return periods, because that's the Tmax that we already had. So we can use to make a plot that looks something like this, where on the y-axis you have the return values, and on the x-axis the return periods that are associated with them. What you could do next is, for example, draw a line through this, or a fitted line, arc or something, and then look for other return periods for which we don't have data, what the return value is, or the other way around. So these are very useful plots, and we'll have a bunch more of those, or look at a bunch more of those throughout this day. However, there may be a few potential issues. One of them, for example, we can find when we look at the most highly ranked, our rank number 1 day, which was in 2019. It was a day which was 37.5 degrees in the build, which is really, really high in the Netherlands. And of course, that has a very low exceedance probability, only 0.008. So there's only 1% chance or something to find that value. But it's based on our record, because you can see that the return value is 122, which is the amount of years that were in our data set. So the highest, it will be very coincidental if, of course, the highest temperature that we found in our record exactly the amount of return, or has exactly the return period that's associated with the length of our record. This has everything to do with the way that we compute them, the formulas that we use, and we could never get a higher return period from, or based on the length of our data. If we only had 5 years of data, then the return period would be 5, which is not exactly the way that we want to estimate these things. The solution to this would be by using the distribution. But however, I already told you we'll do that in a later tutorial. Have a good luck with your exercises, and I will see you in